Hey, the topic today is the first fundamental theorem of calculus. This corresponds to section 5.4 in our textbook. So remember the house of calculus, okay? The foundation is limits. Everything we're doing built upon the idea of limits. Getting closer and closer to a number, but never truly getting there. Then what is the behavior of the function? Is it approaching a single unique value? From that foundation, you have derivatives and you have integrals. Okay, derivatives is the instantaneous rate of change. Integrals, adding those up to accumulate over time the total change. Now linking them together, the roof that attached to the walls that are in the foundation is the fundamental theorem of calculus, kind of how these ideas play off each other. And the first fundamental theorem is right here in yellow. So f(x) is continuous on a to b, and big f(x) is an antiderivative on a to b. Then the definite integral, the integral from a to b of f(x) dx is right here, big F of x from a to b. And you calculate that by doing big F of b minus big F of a. Let's look at how that works out. Start out pretty similar first, and then get into more some of the applications of this. So the definite integral from 1 to 2 of x squared minus 3 dx. Okay, first we want the antiderivative, so x squared becomes 1/3 x cubed minus 3 becomes minus 3x, and evaluate that from 1 to 2. Now, normally we do a plus c, a constant of integration. That is for indefinite integrals, when there are no upper or lower bounds. Definite integrals, you don't include the c, because look back in the yellow box. If you included a c, there'd be a c with big F of b. If you included a c, there'd be a c with big F of a. And then when you just subtracted those, the c's would cancel out. So you don't need plus c with definite integrals. You need them with indefinite but not definite, because you're doing that subtraction. And then we'll evaluate from 1 to 2. So first, plug in 2, so 1/3 2 cubed minus 3 times 2. That's our b upper bound minus big F of a, the lower bound, 1/3 times 1 cubed minus 3 times 1. And then there's a lot of arithmetic involved with these. So some things you can do to kind of help yourself is to write out your work. No, don't try to rush it. Just write things down. And then, usually there's fractions involved. So because of the fractions, you want to get common denominators, adding and subtracting. My advice, instead of writing out a new line of work, kind of in the existing line, get your common denominators. So you're still writing them down, but you're saving some room. Right, so you kind of want to walk a fine balance of writing work, but also writing work efficiently. So 1 minus 9 is negative 8/3. So negative 10/3 minus negative 8/3 become negative 2/3. So area under a curve, we were previously doing only geometric shapes. Now we can do area under a curve of any function we have with an upper lower bound by using the first fundamental theorem of calculus. So the area under the curve of x squared minus 3 from 1 to 2 is negative 2/3. So we can initially kind of see that the majority of the area of this function from 1 to 2 is below the x-axis. The majority of the area is below the x-axis, giving us negatives. Right here for example B, never a bad idea to do a quick rewrite. So 3x to the 1/2 dx. So to get our antiderivative, but I don't like the equal sign, try that again. So increase the exponent by 1, so x to the 3/2, and divide the coefficient by the new exponent. So multiply by the reciprocal, so 3 times 2/3, which would be 2. So 2x to the 3/2, evaluating from 1 to 4. Sorry about that, had to cut it, got a quick phone call. So going back, evaluating from 1 to 4. So then we're going to evaluate the 4, so 2, 4, 2, nope, don't want the fraction there. 4 to the 3/2. Minus 2 times 1 to the 3/2. Now when you evaluate fractional exponents, the numerator is a power, the denominator is a root. So the number goes to the root, gets bigger. The number goes to the numerator, the power, gets bigger. Then to the denominator root gets smaller. Or you can go to denominator root gets smaller, numerator x power gets bigger. You can do either order, make it bigger than smaller or smaller than bigger. I advise you do the root first, then the power. Get smaller, then bigger, versus getting really big from power, then try to get small. So 4 to the denominator, so square root of 4, 2. Then raise to the numerator, a power, to the third. So square root of 4, 2, then 2 to the third, 8. 8 times 2, 16. And 1 is always easy. 2 times 1 to the 3/2, just 2. And you end up with 14. Good deal. Looking at example 2, using the definition of absolute value. So remember, absolute value is a V shape. This equation is going to be shifted to the right a half unit. So we have right here, x is 1/2. Well, it goes up in the V shape to the right and to the left. So our absolute value of 2x minus 1, kind of the definition of that, is you have 2x minus 1, slope of 2, 1 times 1/2, when x is greater than or equal to 1/2. And then you have the opposite, to the left of the v, so right here, you have a slope of -2. Move this around so you can see better. So the left half of the function, there's a negative slope and a positive y-intercept. The entire function is switched around when x is less than 1/2. So to write this definite integral, kind of break it up into two pieces. You have from 0 to 1/2 of negative 2x minus 1 dx. And then you're going to add on from the 1/2 to 2 of positive 2x minus 1 dx. Then evaluate and solve. The mean value theorem for integrals. So let's assume we have a function, okay? Something like this. I could go further, so like that. Then area under the curve would be all the area under the x-axis, or under the curve to the x-axis. So this area all in here. That would be the integral from a to b of f of x dx. Now the mean value theorem says, on that interval from a to b, there must be some value c in there, where f of c gives you a certain height, and that height times the width would equal the actual area under the curve. So for example, let's draw this here. So we kind of draw in the endpoints there and there, and I want to be as specific as possible, so move this over a little. Now the mean value theorem says from a to b, so from a to b, there is some value on the curve, let's say right here. And that c value, when you plug it into the equation, gives you f of c. And f of c, that height, taken over to intervals, gives you an area, some above the curve, the rest of below, so that those two areas are equal. So in this graph on the right, we have f of c, the height, as some c value, times our width, b minus a. And that base times height equals the definite integral. There must be some value in between a and b. That value plugged into the function gives you a height the height times width of that rectangle equals the actual area under the curve. So kind of a existence theorem. There must be some value in there that works. Average value of a function. If you want to know the average value of a function over an interval, pretty simple. Just take the average. The definite integral, right there, times 1 over b minus a. So find the average value of 3x squared minus 2x from 1 to 4. So we want our fraction on the front, 1 over 4 minus 1. And then our definite integral from 1 to 4 of 3x squared minus 2x dx. So we go in a value. So we have 1 over 4 minus 1, or 1/3. Then our definite integral, so 3x squared, and the derivative, x squared becomes x cubed. 3 divided by the new exponent, so 3 divided by 3, 1, okay. And 2x, oh, alright, x squared, easy. And evaluating from 1 to 4. So we have 1/3 of 4 cubed minus 4 squared. And then 1 cubed minus 1 squared. And then just a lot of arithmetic simplifying down. So 4 cubed minus 4 squared. 4 cubed is 64. 64 minus 4 squared, 16. 48. Alright, so 48 minus 1 minus 0. Okay, those all cancel out. So we just have 48. It's almost like they're written to be done by hand. Just checking whether you know the fundamental theories. Then take a look at the rest of the examples in the notes, complete those. Check your work with my completed notes online.